Good afternoon, this is Kavi Priya, Assistant Professor, EC Department, SNS College of Technology. Today I am going to deliver a topic, two topics. First one is Faraday's law and second one is a displacement current. So we have seen about this electric and magnetic fields. So the fields are considered as a time invariant. Whatever fields we have seen so far, it is a time invariant field or it is a static fields. But in time varying or dynamic EM fields, the electric and magnetic fields are interdependent. So static electric fields are produced by stationary electric charges. So the magnetic field is produced by motion of electric charges. So the motion of electric charges with uniform velocity or the magnetic charges produces a magnetic field. So time varying fields are produced due to time varying currents. So Faraday is a person. He is a British physicist and chemist. He is one we discovered the Faraday's law. He is a great experimental scientist. He has a great contribution to the early electricity, which includes his one invention of motor, generator, and transformer. So motor, generator, and transformer was invented by Faraday, and he is one who invented the electromagnetic induction and laws of electrolysis. So in the year 1820, Professor Hans Christian Oersted demonstrated that the compass needle deflected due to electric current. After 10 years, Michael Faraday, a British scientist, proved that magnetic field could produce a current. According to Faraday's experiment, static magnetic field cannot produce any current flow, but with a time varying field, an electromotive force induces which may drive a current in a closed path or circuit. This EMF is nothing but the voltage that induces from the changing magnetic field or motion of conductors in a magnetic field. Faraday discovered that induced EMF is equal to the rate of change of magnetic flux linking with the closed circuits. So whenever there is a change in magnetic lines of force or magnetic flux, an EMF is induced in the circuit. So E is equal to minus N d phi by dt. So where N is the number of turns in the circuit and E is the induced EMF. So negative sign indicates that the EMF induced is an opposite in nature to the change of flux. So for single circuit, we can consider that N is equal to 1. So E is equal to approximately equal to minus d phi by dt. So the minus sign indicates a direction of EMF is to which produces a magnetic field which will be opposite to the original field. In 1834, Henry Frederick Emile Lenz postulated the law. This according to Lenz's law, the induced EMF acts to produce the opposing flux. So let's consider the Faraday's law. The induced EMF is a scalar quantity that is measured in volts. So E is equal to integral over closed path E vector dot dl. The induced EMF indicates a voltage above the closed path such that if any part of the path is changed, EMF will also be changed. So the magnetic flux passing through specified area is given by phi is equal to integral over surface B vector dot ds vector. B is the magnetic flux density. So E is equal to minus d by dt of integral over surface B vector dot ds vector. So by comparing the equation, we can write E is equal to integral over closed path E vector dot dl vector is equal to minus d by dt of integral over surface B vector dot ds vector. So there are two conditions for induced EMF. The closed circuit in EMF is induced is stationary and magnetic flux is sinusoidally varying with time. So from the equation it is clear that magnetic flux density is the only quantity that varies with time. So we can use partial derivative to define the relationship as B may be changing with the coordinates. So E vector dot dl vector integral over closed path is equal to minus integral over surface dou B vector by dou t dot ds vector. So using Stokes theorem, we can convert this E dot dl line integral to surface integral. So integral over closed surface E vector dou del cross E vector is equal to minus integral over surface dou B vector by dou t dot ds vector. So we can equate the surface integral. So del cross E is equal to minus dou B by dou t. So this represents one of the Maxwell equation. B is not varying with time. Then the results we can write it as integral over closed path E vector dot dl is equal to 0. So del cross E is equal to 0. So, and second condition is magnetic field is stationary and constant not varying with time. In such cases, F vector is equal to Q V cross B vector, and EM is equal to E by Q, which is nothing but V cross B vector. So the induced EMF is given by integral over closed line EM dot dl vector is equal to integral over closed path del cross V cross B vector dot dl. If a direction of velocity with the conductor is moving and the magnetic field are mutually perpendicular, then the induced EMF E is equal to BLV sin 90 degree, which is nothing but BLV since sin 90 is 1. L is the length of the straight conductor. The magnetic field intensity is also varying, then the induced EMF is combination of transformer EMF and the generator EMF. So the induced EMF we can write by combining the transformer EMF and the generator EMF. And next is a displacement current, as we know that del cross E is equal to minus dou B by dou T vector dou T. So del cross H is equal to 0, del cross H is equal to J by Ampere's circuitry law. So when we take dot product on both sides, del cross H is equal to, which is approximately equal to 0, which is equal to del dot J. So from this del dot J is equal to minus dou rho C dou V by divided by dou T. Rho V is the volume charge density. From this del cross H is equal to J plus G, where taking a divergence will be getting 0 is approximately equal to del dot J plus del dot G. So del dot G is equal to minus is equal to dou by dou T of rho V. So del dot G is equal to dou by dou T of del dot D, which is nothing but del dot dou D by dou T. So from this we can get the value of G. G is equal to dou D by dou T. So Ampere circuit law in point form therefore becomes del cross H is equal to J plus dou D by dou T. So this addition term dou D by dou T has the dimension of current density. So Maxwell termed it as a displacement current density, which is denoted as JD. So del cross H is equal to conduction current density plus displacement current density. So conduction current density is so it is nothing but J is equal to sigma E is a conduction current density, and displacement current density is equal to dou D by dou T. D is the electric flux density. So del cross H is equal to dou D by divided by dou T in a non-conducting medium. So that's all about electric current density and Faraday's law. Thank you.